Hello and welcome to another video of Wise Interactive Learning. So in the previous video we have went through exercise 6.5 and particularly we have went through 3 questions which are question number 1, question number 2 and question number 3. So in this video we are going to see question number 4 because this is kind of a question which needs us to prove a certain condition, which is that f of x, g of x and h of x, these 3 questions, they do not have any kind of maxima or minima. So in the first and second and the third question, we went through a process. So the process was finding a question, then we needed to find out what is the first derivative test, then we find out what are the 2 turning points, 2 or 3 whatever it is, and then we went on to finding what is the second derivative test. So in the second derivative test, what we saw was if the number was less than 0, then this particular number or this particular turning point gave us a local maxima point, right? So at that particular point we could say that the value of that function was maximum, and if it was greater than 0, then we could say that this was local minima point, right? So we have went through all this terminology and questions, but in these questions we need to have a different understanding or different showing of why such an other conditions do held true. So the first question states that f of x is equals to e raised to x. So if we go through the traditional method or the first derivative test, we can say f dash of x is again derivative of e raised to x. So we knew that the differentiation or derivative of e raised to x is again e raised to x, right? And if we take since therefore we can say if f dash of x, if we equate it to 0, then e raised to x should be equals to 0, and in no condition we can say that this particular question justifies any value of x. So there is no x such that we can find e raised to x is equals to 0. Well, why? Because e is a constant number, right? And if you put any ratio or any number to the power of a constant or a particular integer or a fraction number, you cannot have 0 as its power. The least value which you can have about it can be in any, but it will never have 0 or any kind of negative value, right? So in such a way, now we know that, well, we can't have it. So even if we take f double dash of x, which is the second derivative test, then again we have e raised to x, because since we have a special function which is e raised to x, and if we draw the graph of the function, so beg my pardon, so if we draw something like this over here, so let's say we need to find what is e raised to x. So e raised to x is something like this, which is an exponential function, right? So we only have a point of inflection at somewhere over here, which is x equals to 0, which will equal y equals to 1, which is the value of that function. So we can see that this function e raised to x is an constantly increasing function, right? And since this function is constantly increasing, we have only one point of inflection, which is x equals to 0. So we can write that since x belongs to all real integers or real numbers R, we can say that the function e raised to x do not have any maxima or minima, and since x belongs to R. So this is our proof for finding out whether this particular function does have any maxima or minima. So you can clearly see from this graph that if this graph is of e raised to x, let us say, then this function is going to constantly increase and it is going to keep on increasing till positive infinity. And if you look on to the left side of the graph where x is negative, the value of the y function is going to be always going to be decreasing, but it is not going to touch anywhere y equals to 0. So y equals to 0 is not possible for this particular function. So in the same way, we are going to see what is the maxima and minima for log of x and the third h of x question. So now we will take the second question. So second question says that g of x is equals to log of x. So if we can go through the first derivative test similarly, which is g dash of x is equals to 1 upon x. So if we equate it to 0, 1 upon x equals to 0, we can clearly see that there is no such number for the value of x where we can get the value 1 upon x is equals to 0. So since this cannot be defined, if we exchange the numbers, 1 upon 0 will equals to x, and this is never defined in mathematics, right? So since this is undefinable, which is some we called it as undefinable, we can say that for this particular function log of x, there has to be some kind of understanding of how the graph is moving, isn't it? So if we take the graph of log of x, we can say that this graph moves something like this, where this particular point, if we take this point, so if we take this point, this particular point is a point of inflection, or we can say that it is a point in the graph where the value of that particular function is going to be 0. Well, how it is going to be 0? Let us take a look at it, right? So what is g of x? G of x is nothing but log of x, right? And it says that at x equals to something, this particular value is going to be 0. So what is that x value? X is nothing but 1. How can we say that? If we just take the exponential or antilog of this 0, then we can see that e raised to 0 is going to be x. E raised to 0, sorry for that. E raised to 0 is going to be x. So anything raised to 0 is going to be 1. So x is equals to 1. So we can say that at x equals to 1, this function has the value of 0. But if we take any point before 1, let us take 0.99, and after 1, 1.01, right? So if we take, we can clearly see that this function is increasing function. So it is constantly increasing function for all x belongings to R. So if there is any real number existing onto log of x chart or the graph of it, we can clearly say that this function is an constantly increasing function, and hence since x belongs to all real numbers R, we can say that this function does not have any, so we can write it over here. Since the function log of x where x belongs to R is a constantly increasing function, log of x doesn't have any minimum or maximum value. So this is a proof for why this particular log of x function does not have any kind of minimum or maximum value. Now if we take the third question, which is h of x over here, x cube plus x square plus x plus 1, this is our question. So if we take it, the third question, which is h of x equals to x cube plus x square plus x plus 1. So in order to find out the local maxima or local minima, or what are the local maximum or minimum values of a particular function, what we stated was we drew a graph where we could easily tell that these functions are in an increasing order, right? But in a natural way or a natural intuition where we need to find out the local maximas or minimas of this particular function like x cube plus x square plus x plus 1, it is not feasible for us to actually draw the whole graph and then see that this function is constantly increasing or constantly decreasing. So for this we'll go by standard method, which is finding the first derivative test. So here we have h dash of x as equals to 3x square plus 2x plus 1, right? And then we need to find out if this particular function has any kind of a 0, which means 3x square plus 2x plus 1 equals to 0. So is there any possibility where this quadratic equations has two roots? So let us say that this has two roots, which is alpha plus beta, which should be equals to so the sum and the product we need to find out. So we know that the sum is equals to plus 2 and the product is plus 3. So are there any kind of roots where we find out that the product of the roots is 3 and the sum of the roots is 2? So practically if you look at it, we don't have any kind of combinations. Even if we take 3 and 1 as the numbers, we don't have any solution where it can get to 2, since the sign will be opposite. If we take plus 3 and minus 1, it is going to be, the product is going to be negative 1, and even if you take minus 3 and plus 1, so it is going to be negative 2 as the sum. So since we don't have any real factors for this, we can take the second derivative test. So here we have h double dash of x equals to, and then we can say it is 6x plus 2. Now if we take a look at it, and if we want to plug in the values of x over here, we need to have any rational numbers or any real numbers values from x from this quadratic equation. Since the derivative is not getting to 0, we can say that when x belongs to R, this particular function does not have any kind of maxima or minima. So your solution over here is done.